Here we have a small section of a belt or a rope that is passing over a pulley or a drum or some other object. In this problem there are frictional forces acting on the belt. We are going to analyze the forces acting on just this small section of the belt. So we are assuming that this belt is in equilibrium. So the resultant force on this section is 0. This horizontal line here is just a reference line for the horizontal forces acting on this section of the belt. The belt subtends an angle of d theta. That's this angle here. Now, it is probably better to have delta theta here rather than d theta. D theta is the result of taking limits. So consistent with previous videos in this playing list, I would write delta theta here. The tension in the belt is not constant. We are interested in looking for a formula for the tension in the belt as a function of this angle here. Well, actually this angle is only a piece, the angle subtended by a piece of the belt. The entire angle is the angle subtended by the part of the belt that's in contact with the object, and that angle is beta. So the belt could be in contact all along here, say, and then this angle would be beta. So we look at one small piece of the belt, and since the tension is varying in the belt, since we're dealing with friction here, let's make the tension at this end of the segment T and the tension at this other end T plus dt. Let's assume that dt is positive, so there's a greater force on this end of the segment than there is at this end here. If there was no friction force, then this end would move to the left because this force T plus dt is greater than T. But since we have a friction force, the friction force always opposes motion. So if there's no friction force, the belt would move to the left. With the friction force, the belt is stationary, so the friction force must act to the right. Now, to get the magnitude of the friction force, we need to know the normal force acting on this piece of the belt. So the normal force is the force on the belt due to its being in contact with some object. So the object is down here, it's not shown. So the normal force is perpendicular to this segment of the belt, and this normal force is magnitude dn. Well, again, we probably should use delta n, and when we take limits, delta n becomes dn. But I'll just go back to using dn. Now, it's a fact that the friction force is proportional to the magnitude of dn. The proportionality constant is called mu, the coefficient of friction, and that depends on the surfaces, the nature of the belt, and what the object that the belt is in contact with. Anyway, vector dn is shown down here. We can show it down here as well. Its point of application is here. So we just multiply the coefficient of friction, which depends on the materials, times that normal force dn. Now this line here, which appears horizontal in this diagram, is perpendicular to the bisector of the angle d theta. So this angle in here is d theta divided by 2. Now we will be interested in components of the two tension vectors in a direction parallel to the bisector of the angle and in a direction perpendicular to the bisector of the angle. So we will need to get this angle here. Well, that's actually the same as this angle. These two angles are the same. Why is that? Because the pair of lines that this angle is between, this line and this line here, is perpendicular to this pair of lines. See, this line up here is perpendicular to the bisector of the angle, and this line that T lies along is perpendicular to this line here, because the line that T lies along is tangent to the circle that the belt lies over. The belt is lying over some circular object, so this line is just a tangent to the circle. Similarly, we have that this angle here is d theta over 2, because we're dealing with circular symmetry here. This piece of the belt is a segment of a circle. For equilibrium, the sum of the horizontal or x components of the forces must be 0. So that means that the horizontal components pointing to the right must equal the horizontal components pointing to the left. So we need the horizontal component of this force here. Well, we just multiply t by the cos of this angle. And this force here, mu dn, is entirely pointing to the right. So the sum of these two forces must equal the horizontal component of t plus dt. So that's t plus dt cos d theta over 2. Now dn has no horizontal component. Now we can see that t cos d theta over 2 appears on both sides, so we can cancel that off and we're left with mu dn on the left hand side. On the right hand side we have dt times the cos of d theta over 2. Since the cos of naught is 1, and since d theta over 2 is very, very small and becomes smaller as we take limits, we see that this is just going to be 1. So we end up getting mu times dn equals dt. Now let's look at the sum of the forces in the y direction. Well, mu dn has no component in the y direction, so we can forget about that. dn is pointing upwards, so that force must equal the vertical components of these two forces. These vertical components are pointing downwards. So the upwards vertical components must equal the downwards vertical components. So the downwards component of t is t times the sine of d theta over 2. That's this term here. And the downward component here is t plus dt times the sine of d theta over 2. Now, multiplying out the right hand side, we have t sine d theta over 2 and another t sine d theta over 2. That's 2t sine d theta over 2. And then we have dt sine d theta over 2. Now, when theta is very small, the sine of theta is approximately equal to theta, provided theta is in radians, of course, which it is. So we're dealing with an angle theta that's very close to 0. So what does that mean? It means that we can replace the sine of d theta over 2 with just the angle itself, d theta over 2. So we get 2t times d theta over 2. And we do the same here. Now we get a product of differentials here. So we can just ignore that when we take limits, because dt and d theta are approaching 0, so when we multiply them they just disappear completely. So you see we're left with t times d theta. Now again, we should really be using the delta notation here. All of these d's should be deltas before we take limits. But anyway. Now we can combine these two equations to get rid of dn. So we take the left hand side of this equation and divide it by the left hand side of this equation. The dn cancels out. Then we take the right hand sides and divide. So we end up getting this equation, mu equals dt over t times d theta. Then multiply both sides by d theta, and we get dt over t, which is here, equals mu times d theta. Now if we go back to previous videos, we had this notation here. So instead of dt we had delta t. So we haven't quite taken the limit yet as delta t goes to 0. But we would be summing this quantity from t equals t1 to t equals t2. So one end of the belt is here, and one end of the belt that's in contact with the object, pulley or whatever, is here, and the other end is, say, here. Obviously this is not drawn to scale. This piece here will be a much smaller segment than what's shown here. But we would sum the tensions from the value of the tension here, T1, to the value of the tension here, which is T2. Then we would refine this sum by taking the limit as delta t goes to 0. And as we've seen, all of this here is replaced with an integral sign. We're integrating from T1 to T2, and we replace delta t with dt. Well, that's what we saw in previous videos. And on the right hand side we had mu times d theta. So we would be summing these quantities from the smallest value of theta. Well, theta would run, say, in this direction from a value of 0 here. So this is our reference line for our angle. Theta is 0 here for this end of the belt, and for the other end we'd say the angle is beta. So beta is the angle subtended by the part of the belt that's in contact with the object. So we'd sum from theta equals 0 to theta equals beta, and then we would refine this by taking the limit as delta theta goes to 0. And of course this sigma becomes an integral sign. We integrate from 0 to beta, replace delta theta with d theta, and we get this equation here. Integrating 1 over t with respect to t gives us ln of t, and then we apply the limits. We get ln of t2 minus ln of t1. That can be written ln of t2 over t1. Integrating mu, which is a constant, it depends on the properties of the materials, with respect to theta gives us mu times theta. And plug in the upper limit, we get mu beta minus mu times 0, so we just get mu beta on the right hand side. Finally, we can get the tension at this end of the belt in terms of the tension at this end here. We just take the exponential of both sides. So now we have the tension at this other end as a function of beta. That's the angle between this line here and this line here.